Thank you all for joining this webinar. As Megan said, I will talk about IEC 61000-4-7 standard, which is concerned with determining grid harmonics. And to give a brief introduction and background, let's see. I am with a company called HBK, which is a recent merger of Brüel & Kjær and HBM. And so the merger was made because they were basically two very compatible companies, where Brüel & Kjær used to be working mainly in the frequency domain, and where HBM normally used to work in the time domain. So with this merger, we cover both domains. And so the new company, in the new company, we like to think that we are the product physics experts in the three domains of mechanical, where we measure, for example, strain, load, force, pressure, and torque, etc. The second domain is sound and vibration, where we measure noise, sound quality, harshness of sounds, etc., etc. And last but not least, electrical, where we measure electrical signals, voltages, powers, and combining all those domains, we can, of course, do much more, for example, determine efficiency, etc., etc. So that is the background of the company. My own background is that, as Megan said, I am product owner of the Genesis high-speed perception eDrive solution product, where we are combining electrical measurements with noise and vibration measurements, but also with mechanical measurements. And so I am senior product owner of this product, and my current focus is on frequency domain methods, such as I will talk about in this presentation. But we are also I'm also working on frequency domain methods for eDrive applications. So that is the background of this presentation, so that you know where I'm coming from. So now we're going to the more technical part. We are going to talk about the power grid. So what is the power grid, and how is the power grid recently changing, and what are the consequences of those changes? Then we are going to talk about harmonic analysis according to a dedicated standard, the IEC 61000-4-7 standard, which prescribes how we should measure e-grid harmonics. And I will go into quite some detail on how that should be done. And then I'm giving a practical example of how you can measure grid harmonics, and then I'm closing with a summary. So off we go. First, I'm going to talk about the power grid. So, of course, as we all know, the power grid is the infrastructure that generates and distributes electrical power, often over a very large area. For example, this can be a country, but it can also be across countries. So that is the infrastructure of the power grid. What we now see happen recently, and this will continue for the time to come, is that we will see significant changes in the use and the structure of the power grid. For example, due to developments like there will be an increasing demand on electric power due to increasing electrification. Where you can think of, for example, then, is that we all know that cars more and more will no longer use fossil fuels, but they will use electricity. So the batteries must be charged, and that requires electric energy. But also there are other domains, not only in vehicles, but also other domains where we want to reduce the CO2 that we generate. So that means that many applications, not only vehicles, but many applications will go to electric. And that is a bit on the demand side, but what you see on the supply side is that also the infrastructure of the power grid is getting more complicated. So where you used to have, let's say, a relatively small number of very large electrical power plants, now you have a much more diverse structure where you still have those very large power plants, but you also have medium-sized and small providers of electric energy, where in medium size you should think about, for example, windmill parks, solar farms, etc. And if you look at a very small scale, many of us at home have solar panels on their roof, and of all the electric energy that we generate, we only partially use that ourselves. So the rest of the surplus energy is provided back to the power grid. So that is also a major change that is happening in the power grid that is currently going on, and that will continue in the near future. And that has also a consequence that is kind of perpendicular to this, and that is that if you look at all the devices that are connected to the power grid, they are getting much more complicated, and they are offering much more diverse loads to the grid, and that has consequences for power quality. So if we look at the power grid aims at delivering electric power in the form of a sinusoidal 50 or 60 hertz AC voltage. And of course, if you want to generate power or if you want to absorb power from the power grid, you also have to have the resulting current. But the basic idea is that depending on the country you are in, the power grid is aiming at 50 or 60 hertz sinusoidal signals in terms of power supply. And in a few decades ago, when the loads or when the devices connected to the power grid were still very simple, like incandescent lamps, traditional heating equipment, but also certain types of electric motors, all the voltages and the currents that were in the power grid, they remained sinusoidal signals, because basically all those loads, they were very decent, they were very resistive and very linear. So if you started out at a power plant with a sinusoidal voltage, then you kept sinusoidal voltages and you kept sinusoidal currents. So what you would see then, if you would look at a voltage or at a current, that would be a very nice sine wave, as you can see in the top picture here. And if you would look at this signal in the frequency domain, you would have a very nice spectrum. You would have a single spectral component at 50 hertz only, or at 60 hertz when you are in the 60 hertz area. But so at this point in time, life was still quite simple. But as I mentioned, recently, over the past decades, much more complicated loads are connected to the power grid. And you can think, for example, of variable frequency drives, transformer, electronic ballast, but also LED lights, microwave ovens, photovoltaic inverters, switch mode power supplies, etc., etc. They are no longer, let's say, very nice linear loads. So if you attach a device to the power grid, then your signals will no longer be sinusoidal. Neither your voltages, neither your currents will be sinusoidal. So what you will get, for example, if you put a linear and or switching load to your power grid, you get a voltage or a current that looks still a bit like a sine wave, but is not really a sine wave. So there is a deviation in your power and current signals from your ideal sine wave. And this deviation from a perfect sine wave can very well be expressed in terms of harmonics. So if you look at this kind of sine wave time signal, if you then look in the frequency domain, it looks something like this. So of course you still have a very strong 50 hertz component, but next to this 50 hertz component, you also have a lot of other spurious frequencies, and those are called harmonics. And they appear at frequencies that are multiples of your fundamental frequency. So in this case, they appear at frequencies of 100 Hertz, 150 Hertz, and 200 Hertz, etc., etc. And this can go on quite far. So you can have quite high frequencies. So this distortion, or those spurious frequencies, they are generated by certain devices, equipment connected to your power grid. But then if I connect another device, this device will no longer see a perfect sine wave. It will see a sine wave as, or a time signal as depicted in this slide. So harmonics caused by one piece of equipment can have an impact on other equipment connected to the grid in terms of, for example, what will happen if you have harmonics in your signal. Well, if you have harmonics in your power signal, this will lead to additional losses, and those additional losses will lead to higher temperatures. And those higher temperatures may lead to shorter lifetime, lower efficiency, etc., etc. And those losses that are introduced by those spurious harmonics, they can have several causes. And I mention a few. First is the skin effect. So if you send a current, for example, a 50 Hertz current through a conductor, then of course that current encounters a certain resistance. But now if you, for example, send a current with, let's say, 200 Hertz through the same conductor, what you will see is that the current is pushed to the outside of the conductor. And that in effect means that the resistance of the conductor for that frequency increases, and that increases losses. So you have two effects. The first effect is that you have a harmonic that you actually don't want, and that harmonic that also has experiences the skin effect. So the losses that you have because of this harmonic are larger than the losses that you have, relatively speaking, from your fundamental. So that is something that you don't want. So that is one of the causes of additional losses caused by harmonics. A second effect is that you have magnetic losses. So if you have magnetic materials in your device, then every time you go through a single cycle of your current, then you lose energy because of magnetic properties. So every time you go through such a kind of loop, you lose the energy relative to the area of this curve. And of course, if you have a harmonic that has a higher frequency, in a certain time, you go more often through this loop. So you lose more energy if you have harmonics. So the loss in the magnetic losses due to harmonics, they are proportional to the frequency. So it's getting worse with higher harmonics. And last, then there's an effect called eddy currents. So if you have a magnetic field, for example, in a motor, and if you have a conductor close by, then a changing magnetic field introduces eddy currents in the conductor, and that currents that also has conductor has resistance, so that will also cause losses. And eddy currents, they go even with the square of the frequency. So all those effects caused by harmonics, they all lead to additional losses in your device, and that is normally not a good thing. Another effect that you might have, for example, if your device is a electric motor, certain harmonics may lead to negative torque components. And if you want to have a certain torque at your axle and you have a harmonic causing a negative torque component, then your primary torque component must be increased. Otherwise you have a lower torque at your axle. So all those things are negative things caused by additional spurious harmonics in your power grid. So therefore, it is very important to be able to characterize and measure harmonics in power grid signals in a well-defined and standard manner. And why is that necessary? Well, it allows to define limits on the maximum amount of harmonic energy in grid signals. So harmonics are things that you don't want, but you cannot always avoid them. So therefore, it is very useful if you can measure harmonics in a standardized way, and then, for example, certain institutes, they can say, okay, this device is acceptable to be sold, for example, because the harmonics that it generates on the power grid are below a certain level. So that is very important. And basically, the IEC 61000-4-7 standard does exactly that. So what does this standard do and what does it define? Well, the IEC 61000-4-7 standard defines how harmonics should be measured for 50 and 60 Hertz power grid or power line signals. So it tells you how you should measure those harmonics. And one of the things that it says is, well, this is the total official title of that standard. So it is testing and measurement techniques, and it's a general guide on harmonics and interharmonics. I will talk about it later. Interharmonics measurement and instrumentation for power supply systems and equipment connected thereto. So it is really targeted at power grid and power line signals. So what this standard does not prescribe is the limits. So in my previous slide, I talked about the limits. This standard, the 61000-4-7, is not concerned with limits. It is only concerned with how you should determine the harmonics in your power grid signal. But still, it's a very important standard because many other standards refer or use this standard. For example, the 61000-3-3 and -3-13. Those are standards that impose limits on harmonic current emission for equipment connected to the power grid to maintain a certain voltage quality. So you can say that the IEC 61000-4-7 standard is a very basic standard because it prescribes how you should measure harmonics, measure and calculate harmonics in power grid signals. And then what does the standard say then? What does the standard say about how you should measure harmonics? Well, there are several components to that, and I will not go through all of them in detail, but I will mention a few. So the first thing that the standard prescribes is that in order to determine the harmonics, you should always take a time signal that contains 10, in case of 50 Hertz signals, or 12 periods of the power grid signal as your analysis window. So what it looks like is the following. So for example, if you have a 50 Hertz system or a power system with a nominal frequency of 50 Hertz, the standard says that you should take a time signal of 10 periods, which is then approximately 200 milliseconds. And this time signal you should use to determine your harmonics. So it's not allowed to determine the harmonics, for example, using a single period or 2 periods. You should always use 10 periods in case of a nominal frequency of 50 Hertz and 12 periods in case of a nominal frequency of 60 Hertz, so that in any case you always end up with a time signal of approximately 200 milliseconds. So that is one of the things that the standard prescribes. Another thing is that it is not allowed to have gaps between your windows. So if you have measured, for example, from 0 to 200 milliseconds, and you have determined your harmonics for that time signal, the next set of harmonics should be determined on the next 200 milliseconds, etc., etc. So it's not allowed to determine the harmonics over 200 milliseconds, then take a break for 200 or 350 milliseconds, and then take the next 200 milliseconds. That is not allowed. It is not allowed to have gaps between the different analysis windows. So that is what the standard prescribes. Of course, if you're talking about harmonics live in the frequency domain, you should deploy in some shape or form a Fourier transform to bring you from the time domain, so from your time signal of 200 milliseconds, to bring you to the frequency domain. So it is in very many cases when you are going to the frequency domain, so you have a time signal and you're going to the frequency domain, what is done in many cases, and that is perfectly fine in those cases, what you're doing there is time window. For all kind of technical reasons, you're first applying a dedicated time window to your time signal, and only after that you are going to the frequency domain. For people who are or have been working in that field, I'm talking about Honning windows, Blackman windows, Humming windows, etc., etc. But the standard, the IEC 61000-4-7 standard, says it's not allowed to do time domain windowing. So you should take your time signal, and without any further ado, you should translate that time signal to the frequency domain. So it's not allowed to have time domain windowing. The frequency range that you should be able to handle is up to 9 kilohertz, but for the harmonics only, it's sufficient to go up to 3 kilohertz. So that is what is required. And of course, if you look at power grid signals, we are normally talking about nominal frequencies of 50 hertz or nominal frequencies of 60 hertz, but of course in real life those frequencies are never exactly 50 hertz. So if there is a very big load on the total power grid, your frequency will be slightly lower than 50 hertz, and if your power grid is only very lightly loaded, maybe during the night or something, then your frequency will be slightly higher than 50 hertz, but it's always in the order of 50 hertz. But what the standard prescribes is that the measurement equipment or the device that you are measuring with should be able to handle at least plus or minus 5% of the nominal frequency. So in practice, that means that when you're measuring this for a nominal 50 hertz systems, you should be able to handle frequencies from 47.5 to 52.5 hertz, and for 60 hertz systems from 75 hertz to 63 hertz. So those are, let's say, important things that the standard prescribes on how you should measure harmonics. There are more details, but I'm not going into that because they're not so relevant. Well, okay, we're diving into a bit more detail. So what the standard says is that we have to take 10 or 12 periods. But if we do that and we go to the frequency domain, then we get a spectrum. And what you then see in the frequency domain is that what you may call the pure harmonic, they appear at multiples of 10 of your frequency components, or 12. So if you have a time signal of 200 milliseconds, then the frequency resolution in your spectrum is 5 hertz. So if you want to go from 0 hertz, so DC, to 50 hertz, then you have to make 10 frequency steps. And that is shown in this picture here. So if you take 10 periods in your time signal, then you get a spectrum that looks something like this. So you have a large number of frequency components, but only every 10th is a multiple of your nominal frequency. So you have 50 Hertz and 100 Hertz, but you also have 55 Hertz and 60 Hertz, etc. And what the standard says is that what I call the pure harmonic frequencies that are called by the standard harmonic frequency components. So they are dark blue in this slide. And all the frequency components between them, they are called interharmonic frequency components. So if you go from the time domain with 10 periods to the frequency domain, this is what your spectrum looks like. So this is not yet the harmonic. So this is what your spectrum looks like. But we are not so much interested in the spectrum, we are more interested in the harmonics. So the standard using a technique called spectral grouping. And it has 3 flavors of that. And in this slide, I will briefly mention them. And then after that, I will go into more detail of what all those different methods mean. So bear with me. So the underlying idea is that in spectral grouping, you are not only taking the energy in the spectral lines at the pure harmonic frequencies, but you also take the energy in the neighboring interharmonics. And then you have 3 flavors. First is that you do no grouping, so you are only looking at the pure harmonics. The second one is sideband grouping. In that case, you take the right and left neighbor. And the last one is full grouping. But in the next slides, I will go into detail of how that works. So this is the first flavor. This is no grouping. So again, at the top of this slide, you have the spectrum, which is the same picture as in one of my earlier slides. And if you are using no grouping, the harmonics are determined by just taking the harmonic frequencies or the pure harmonics. So the first harmonic, the 0th harmonic, is the DC frequency. The first harmonic is only the frequency bin at 50 Hertz. The second harmonic is only the component at 100 Hertz, etc., etc. And what you also see, if you have looked at spectral images, those are normally a bit squiggly lines. But in harmonics, it's customary to display the harmonics as a bar chart, which is done at the bottom of this page. And it's also no longer custom to put at the horizontal axis the frequency, but it's more common to put the number of the harmonic. So the first harmonic and the second harmonic, etc. So that is common. But just to summarize, when you are using no grouping, you are only using the frequency components at 0 Hertz, 50 Hertz, 100 Hertz, 150 Hertz, etc. So that is the flavor no grouping. Then you have the second flavor that is called sideband grouping, or in the standard it's called that they are using the harmonic subgroup. So if I first look at the second harmonic, which is in the middle of this slide, then what I'm doing is that I am generating the harmonic, so in the bottom picture, by using the energy in the 100 Hertz component, but also in the component one left of that and one right of that. So I'm combining the energy of 3 spectral components, and that forms my second harmonic. And I'm doing the same for 50 Hertz. It's not drawn here because otherwise it gets cluttered. But also to determine the first harmonic, I'm taking the 50 Hertz component and the component left and right of it. And I combine the energy, and that is the energy in my first harmonic. And in DC, it's slightly different because I don't have a component left, but the underlying idea is the same. I'm taking the main component, so the 0 Hertz component, and one component right of that. So this is how you determine harmonics based on sideband grouping. And then the last one is full grouping. So I'm doing something very similar, but I'm taking more sidebands. And a point of attention here is that in this case, I am using only half the energy of this component to determine this harmonic. and the other half of this energy is used for this component. So what I'm doing in the end is, in order to determine my harmonics, I am retaining all the energy that I had in my spectrum, and all that is the same as all the energy that I used to have in my time signal. So in this case, I'm using only half the energy for the second harmonic and half of the energy in my third harmonic. So those are the different flavors of spectral grouping. Why would you like to do spectral grouping? Well, the standard motivates that as follows. Spectral grouping assists in ensuring that the total power is for most part accurately preserved in cases when the fundamental frequency and the amplitude change over time. So in the standard they also give a very nice example. So what you see on the bottom left is a fifth harmonic sine wave, but and the frequency does not change, so it is always the same, so it's always 250 Hertz, but the amplitude changes at some point in time. And now I am interested in what is the energy in the fifth harmonic. Well, I can calculate in the time domain what the RMS value is of the fifth harmonic, and that turns out to be 2.367. So that is mentioned here. Now, if I now calculate the fifth harmonic, and I do that without grouping, so in the flavor no grouping, then I'm ending up with an RMS value that is 1.909, which is a deviation from the true value of 9.3%. So that is quite a big error. If I use sideband grouping, I do slightly better. Then I have an error of 3.84%. And when I use full grouping, I'm doing even better, and then I have an error of 1.47%. So this is the underlying motivation of grouping, to retain as much energy in your harmonic as possible. But still, you have the choice to choose either no grouping or sideband grouping or full grouping. So that is the underlying motivation why the standard prescribes grouping. The standard also prescribes entities that can be seen as a summary of the total harmonic content or the total harmonic pollution. Given the harmonics derived with any forms of grouping, those additional quantities are defined as follows. I think the first one is very well known. That is the total harmonic distortion, which is the ratio of the energy in all the harmonics except the fundamental divided by the fundamental. And the standard allows to put a upper limit, in this case K max, to the number of harmonics you want to take into account. And the second one is the partially weighted harmonic distortion, the PWHD, which is similar but a slightly different form. The higher harmonics are weighted heavier in the total summary. As I said here briefly, for the THD, I'm talking about harmonics. So as I mentioned, I can calculate the harmonics in three different ways: without grouping, sideband grouping, and full grouping. So if I know that, then I also have three flavors of my THD, namely based on harmonics calculated using no grouping, sideband grouping, and full grouping. So I have three flavors of my THD, and in the same way I have three flavors of my PWHD. So that depends then on how you calculate the harmonics. Okay, then we are going into measuring grid harmonics. How do we do that? Well, in our solution that we have implemented all those functionalities such that it can be very easily used. What we are doing is in our solution, of course, we follow the standards. So every time we are measuring off 10 cycles, and then we are generating the harmonics. And in our solution, we are doing that based on a technique called cycle detection. So we measure 10 cycles, and then we are generating the harmonics. And then we measure the next 10 cycles, and we generate the harmonics. But for the user, all this is made very, very easy. So to start with, we provide, as we are also doing in the context of eDrive, but now also in the context of eGrid, we are providing a number of ready-to-use application templates. For example, you see here a typical application template that you may want to use to measure a PV inverter. So you have a DC source, which are the solar panels. Those are going into an inverter, which is generating a 50 hertz sine wave from that, and then that is going into the power grid. And you may want to measure at this point, so where the inverter is sending its power to the power grid. At this point, you may want to be interested in how many harmonics you are inserting into the power grid. But also other things like you have a regular device, maybe a washing machine or a electric motor, which is connected to the power grid. You may want to measure how many harmonic content that this device introduces in the power grid, etc., etc. So in total, we provide 8 ready-to-use application templates, which are a very good starting point for your measurement setup. But of course, they are not fixed. You can change them and store them, whatever you want to do. So we are just in this approach, we are just following what we have done for years in the context of eDrive. So ready-to-use application templates. And those application templates, they take care of everything. So under the hood, we have to do all the processing. So we have to measure the 10 cycles. We have to process that time slice to generate spectra, etc. All those formulas that you need are automatically generated. For example, what you see here, under the hood, we have a dedicated function that is called Harmonics IEC 61000 that takes as an input a time signal and a cycle signal, and as an output it generates a spectrum according to the standard, which is then further processed. So you don't have to type in all those formulas. It's all done for you when you are using application templates. And as always, all the formulas are completely visible, transparent, and you can edit them if you want. So it's all easy to use and very transparent. And when you have finally done that, you can see the results in a dedicated display where you can see the time signals. So in this case, you have a 3-phase power system with 3 currents and 3 voltages. And next to that, you can see the harmonics calculated according to the standard. And so you can see in real time what is going on with the harmonics in your currents and in your voltages. One nice feature, I think, is that, of course, you can see all those signals in real time. And if you see those signals in real time, you will probably have made a choice. For example, I want to have the harmonics calculated using full grouping. And that is fine. And then you see immediately you see the result of full grouping. But after you have finished your recording, you can reprocess the signal. So you don't have to redo your recording. You can reprocess your signals based, for example, on no grouping or on sideband grouping. So that is true for the bar charts and the tables that you see. So you can very easily change the way that you measured full grouping to, for example, no grouping, and then you get a different set of harmonics, different heights at least. And you can do the same for the THD and partially weighted harmonic distortion. So after the fact, you can still change the number of harmonics that you are using for THD and also what type of grouping that you are using. So that gives you a lot of flexibility after the fact. So we think that's a nice feature. And of course, but that comes with the total solution. Besides looking at the sheet for harmonics, you can, at the same time, you can look at other views of your signals. For example, if you have a 3-phase power signal, you can use the existing phasor plots, for example, to see what your phasors are doing. And then maybe you can get information about a certain phasor configuration, how that maybe impacts the harmonics, etc. etc. So you can do that all in real time, but also in review later on. So all in all, we think that that gives a very nice and flexible solution. So coming to the last part of my presentation, the summary. So what we have seen, we see an increase in nonlinear and or switching loads, and they produce harmonics in the power grid. Harmonics have a negative impact on other equipment connected to the grid, for example, due to additional losses, higher temperatures, etc., etc. The IEC 61000-4-7 standard describes how harmonics in power grid and power line signals should be determined. And I discussed a solution on how that can easily be done. So that is basically it. If you want, you can join us on YouTube or LinkedIn. And if you have questions, then please don't hesitate to contact me. Thank you.